There is a question that has sat at the edge of archaeology for over a century, not because no one has thought to ask it, but because the people best positioned to answer it had too much to lose by asking it honestly. It is a question carved into the stone itself, waiting in the walls of quarries that have been open to visitors and researchers for generations, written in a language of curves and surfaces and microscopic traces that the human eye can see, but the human mind, trained and credentialed and professionally invested, has consistently found ways to explain away. The question is simple. How did they actually do this? Not how could it theoretically have been done. Not how might a determined enough workforce with unlimited time have eventually produced something resembling this result. But how, specifically and mechanically, were these marks made, these particular marks, in this particular stone, with this particular level of consistency and precision, in locations where a human body cannot physically operate? That question has lived for a long time in the uncomfortable silence between what the textbooks say and what the stone actually shows. In 2024, it was handed to something that had no reason to stay silent. A machine intelligence with no reputation to protect, no academic lineage to honor, no colleagues to disappoint. It was shown the evidence and asked to give its honest assessment. What it said did not refine the existing story. It demolished it. To understand the weight of what that assessment means, you have to begin where the stone begins, in the quarries of Aswan in southern Egypt, where the Nile narrows between banks of exposed granite and the desert starts immediately beyond the thin green border of the floodplain. This is where the ancient world came when it needed its hardest and most impressive material. The granite extracted from these quarries traveled north along the river to become the inner chambers of pyramids, the columns of temples at Karnak and Luxor, the towering obelisks that once punctuated the skylines of the great ceremonial cities, and the colossal statues whose faces have stared across the sand for thousands of years, indifferent to the civilizations that rose and fell around them. The stone these quarries produced is not the kind of material you can work casually. Aswan granite sits between 6 and 7 on the Mohs hardness scale, the standard measure of a mineral's resistance to being scratched. That range places it above almost every metal tool available anywhere on Earth during the period when these quarries were most actively used. Copper, the dominant metal of early dynastic Egypt, sits far below granite on that scale. Bronze, which represented the great metallurgical advancement of the ancient world, does not come close either. You cannot carve into a material that is harder than your carving tool. The tool gives way first. The stone survives untouched. This is not a minor technical inconvenience. It is a fundamental physical barrier that stands between any account of how this granite was worked and the reality of what tools these people demonstrably had access to. For generations, the solution offered by mainstream archaeology was elegant in its simplicity and deeply reassuring in its implications. The ancient Egyptians, the story went, shaped their granite not by cutting it but by pounding it. Workers wielding balls of dolerite, an igneous rock harder than the granite itself, would hammer the surface repeatedly, crushing it grain by grain, lowering it slowly through patient sustained percussion until the desired shape emerged. Researchers actually tested this method. They took dolerite balls, sat down in front of real granite surfaces, and hit them repeatedly, and they proved that yes, the process does work. Granite does yield to sustained pounding. Given enough people and enough time, you can produce a trench, a channel, a shaped surface. The method is real. It functions. On paper, the mystery was closed. But paper is not stone. And the marks left by those modern experiments in pounding did not look like the marks in the Aswan quarries. They looked nothing like them at all. When you pound granite with dolerite, you produce a characteristic kind of surface damage. The stone fractures along its crystalline grain boundaries. The result is rough, irregular, and chaotic in the way that any impact against brittle crystalline material is chaotic. You get pits with fractured edges, crushed zones where multiple grains shattered simultaneously, and a general texture that reflects the violence of the method. The surface shows the history of every individual blow, each one slightly different in angle and force and contact point, each one leaving its own unique signature of destruction. The aggregate of thousands of those blows is a surface that looks worked, but worked the way erosion looks worked, through accumulated random force rather than through guided precise intention. The marks in the Aswan quarries do not look like that. Anyone who has stood in front of the quarry walls and looked carefully, anyone who has run their fingers along the surfaces rather than simply photographing them from a distance and moving on, has noticed the same thing. The marks are smooth. They curve in consistent arcs. They repeat with a regularity that does not belong to any process involving a human arm swinging a heavy object at a hard surface. They look less like the scars of percussion and more like the traces of something that passed through the stone in a controlled continuous motion, removing material in a steady sweep rather than shattering it in a violent impact. The most dramatic concentration of these marks surrounds the most famous object in the quarry. The unfinished obelisk is a single piece of granite that, had it ever been successfully freed from the bedrock, would have weighed more than 1,000 tons, making it the largest obelisk ever attempted anywhere in the ancient world. It was abandoned midway through its creation when cracks spread through the granite and rendered it unusable. The workers simply left it where it lay, still partially attached to the living rock beneath, surrounded by the channels they had been cutting to free it. That abandonment froze a moment in time more completely than any excavation could. The process of cutting was simply stopped and left exactly as it was, and the walls of those channels are covered in scoop marks, dozens of them, hundreds of them, each one between roughly 6 and 8 inches across, each one sinking 2 to 4 inches into the granite surface, each one following the same smooth consistent curve. Not similar curves. The same curve. Over and over, covering vast areas of the quarry face. This is what has sat in plain sight for more than a century. And this is what was given to a machine intelligence in 2024 with a single instruction. Look at this without assumptions and tell us what you see. The system used was Grok, developed by Elon Musk's artificial intelligence company, XAI. The choice of tool mattered less than the approach taken with it. High-resolution photographic imagery of the Aswan quarry marks, detailed enough to show individual grain textures within the scoops, was provided to the system along with a deliberately stripped-down prompt. The researchers did not tell it what period these marks dated from. They did not mention pharaohs or copper tools or the accepted archaeological consensus about ancient Egyptian stoneworking methods. They did not load the question with any of the contextual weight that a human expert inevitably brings to a familiar subject. They asked it, in the most functionally neutral terms they could manage, to compare what it was seeing against everything in its training data about how surfaces get cut, shaped, and processed, whether by ancient methods or modern ones, and to report what matched. The power of this approach lies in what it removes. A human archaeologist looking at the Aswan quarry marks is not looking at them fresh. They are looking at them through decades of training, through the consensus of their field, through the awareness that certain conclusions are professionally acceptable and others are professionally dangerous. They see the marks through the story they have already been told about the marks. A machine intelligence has no such story. It has an enormous library of pattern information drawn from across human knowledge, but it has no career investment in any particular interpretation of what it is examining. It compares what it sees against what it knows and reports the closest match without the self-protective filtering that shapes how human experts present their findings. What Grok found when it examined those images was unambiguous. The surface characteristics of the Aswan scoop marks did not match the signatures of percussion. They matched the signatures of rotational cutting. The difference between these two processes is not subtle. Percussion, striking a surface repeatedly with a hard object, produces fractures. The energy of impact radiates outward through the stone's crystalline structure, and the material fails along its grain boundaries in irregular, unpredictable patterns. Rotational cutting, moving a tool in a circular motion across a surface, produces smooth, continuous arcs. The material is removed progressively rather than shattered suddenly. The result is a surface that curves cleanly and consistently, exactly the way the Aswan marks curve. The system's conclusion was direct. The marks were consistent with a rotary cutting process. They were not consistent with hand-delivered percussion. The old explanation was not inadequate. It was wrong in a specific and measurable way. The analysis did not stop at qualitative pattern matching. It moved into numbers, because numbers do not accommodate interpretation the way qualitative descriptions sometimes do. A numerical analysis either shows what it shows or it does not, and the numbers that emerged from examining the Aswan marks are among the most difficult pieces of this entire puzzle to dismiss or reframe. When researchers or casual visitors look at the scoop marks covering the quarry walls, the immediate impression is of marks that are roughly similar to each other. Similar in size, similar in shape, similar in spacing. That impression of similarity is accurate, but it dramatically understates how similar they actually are. The system measured the marks systematically, cataloging the width of individual scoops, their depth, the radius of their curved profile, and the interval between one mark and the next. It built a dataset covering thousands of individual measurements and then asked the most straightforward possible question. How much do these values vary? In handwork of any kind, variation is the rule. No human being swinging a tool produces identical results on consecutive strikes. Fatigue changes the force delivered. Shifting body position changes the angle. Variations in grip change the point of contact. Even the most skilled and disciplined craftsperson produces scatter in their measurements. That scatter is not a flaw or a failure. It is simply what human physical action looks like when you measure it precisely. It is the signature of a living body doing work. The scatter in the Aswan marks was not there. Across extensive areas of the quarry face, the width of individual scoops varied by less than 5% from the mean. The depth varied by comparable amounts. The spacing between consecutive marks held to within 3%. And the radius of the curve, the single most revealing measurement because it is the one most directly determined by the geometry of the tool that made the cut, did not vary meaningfully at all. Across thousands of marks covering walls the size of buildings, the cutting radius was effectively constant. 5% variation sustained across thousands of repetitions is not the output of a human arm. It is the output of a process that is mechanically constrained, where something other than human judgment and human muscle is governing the position, depth, and motion of the cutting tool. 3% variation in spacing suggests indexing, the systematic advancement of a tool by a fixed increment, the way a machine moves from one pass to the next rather than the way a worker eyeballs the gap between one blow and the previous one. The constant cutting radius points to a tool with fixed geometry, something rotating around a fixed point rather than swung in the variable arc that a human arm describes. The system labeled the pattern with a term that the archaeological community has not historically been comfortable applying to ancient stonework. It described the marks as exhibiting non-human precision, not supernatural, not extraterrestrial. Non-human in the strict technical sense that the tolerances exceeded what unguided human physical action can produce, even under ideal conditions, even from the most skilled workers imaginable. What makes the physical evidence even harder to absorb is where some of the marks appear. The distribution of scoop marks across the Aswan quarries is not limited to open, accessible surfaces where a worker could stand comfortably and swing a tool with reasonable freedom of motion. Some of the marks appear in locations that create serious problems for any explanation based on human physical action. There are marks in tight interior corners where two cut faces meet at angles so acute that there is no room for a backswing. Percussion requires clearance. To deliver a blow, you need space to draw the tool back before bringing it forward. In these corners, that space does not exist, yet the marks continue through them with the same smooth consistency found on the open surfaces, flowing into the corner and continuing on the adjacent wall as though the geometric constraint meant nothing. There are marks on surfaces in confined spaces where no human worker could fit. The marks disappear into gaps between partially extracted blocks and the bedrock beneath them, running into slots too narrow for a hand to enter, let alone a tool being actively wielded. They are simply there, deep in spaces that are physically inaccessible, showing the same smooth curves and consistent dimensions as the marks on every open surface around them. There are marks on near-vertical faces at heights that would require a worker to be suspended in mid-air in an awkward contorted posture, delivering not one or two blows but thousands of them with the sustained consistency the surface actually shows. And there are the deep narrow shafts, test pits that descend straight into the granite to depths of 30, 40, and 50 feet while remaining only 3 or 4 feet wide. Picture that geometry. A shaft deeper than a four-story building is tall, narrow enough that a person at the bottom could touch both walls simultaneously. The official explanation describes these as exploratory shafts sunk to test granite quality at depth before committing to major extraction work. That explanation is reasonable as far as it goes. What it does not explain is how you pound granite into a perfectly consistent narrow vertical shaft 40 feet deep in near-total darkness with no room to swing anything. When the system analyzed the paths those shafts actually took through the rock, it found something that had apparently not been widely noted before. Some of the shafts do not descend in straight vertical lines. They curve as they go deeper, drifting in directions that correspond, when compared against later geological surveys of the site, to the internal mineral structure of the granite itself. The shafts were tracking the natural grain of the stone, following veins and planes of weakness that run through the rock in directions that cannot be seen from the surface and cannot be known in advance by anyone working from the top down by hand. The cutting followed the internal geology of the material as though whoever or whatever was making the cut could see through solid rock to the structural features hidden inside it. When the analysis moved to microscopic examination of the cut surfaces themselves, the final layer of the conventional explanation came apart. Under electron microscopy, a surface that has been shaped by percussion shows a characteristic texture. The grains at the surface are crushed and fragmented, their edges irregular and sharp, the fracture patterns radiating outward in the chaotic geometry of impact damage. That texture is the microscopic signature of being struck repeatedly with a hard object. It is what the pounding theory predicts, and it is what should be visible everywhere at Aswan if the pounding theory is correct. It was not what the analysis found. The cut surfaces at Aswan showed faint spiral patterns sweeping across them, barely visible arcs that repeated at consistent intervals. These are the traces left by a rotating tool, the same kind of marks a drill bit or a milling head leaves when it cuts through material, the path of the cutting edge repeated over and over as the tool turns. More significantly, some individual mineral grains at the surface showed signs of partial melting at their edges, zones where the crystalline structure had softened and the boundary between adjacent grains had blurred. Cold impact cannot produce this effect. You cannot pound granite hard enough to melt it locally. Localized melting of this kind requires heat, and the kind of heat that can melt the edge of a single mineral grain in granite while leaving the surrounding material intact is the heat generated by friction, by a tool moving across or through a surface at very high speed. Trace chemical analysis of residues within the cuts identified two materials in particular: diamond dust and corundum, which is crystalline aluminum oxide. Both substances are among the hardest known to exist on Earth. Both are used today in precision industrial cutting and grinding applications. Diamond-tipped rotary tools, grinding wheels loaded with corundum abrasive, water jet cutting systems, ultrasonic machining equipment. These are the modern processes whose surface signatures most closely matched what the analysis found in the ancient stone. Every one of them is a product of industrial technology. Every one of them is, according to the accepted timeline of human technological development, impossible in the period when these marks were supposedly made. And then there is the detail that reframes everything that came before it. In various locations across the Aswan quarries, the granite surfaces bear paintings. Red ochre images of birds, boats, human figures, and geometric symbols, the work of people whose presence at the site predates the dynastic period. These are prehistoric markings, typically dated to somewhere between 6,000 and 4,000 years before the Common Era, painted by people who lived and moved through this landscape long before the institutions of pharaonic Egypt existed. They represent some of the earliest evidence of human symbolic behavior in the region. In several locations, those prehistoric paintings sit on top of the precision scoop marks. The paint is applied over the cut surface, which means the cutting was already there when the painter arrived. The marks are older than the paintings. And if the paintings are prehistoric, then the cutting that underlies them is older than prehistoric. It predates the dynasties. It predates the Old Kingdom. It may predate any period that our current archaeological frameworks have names for. The systems analysis of the sequence of work across the quarry produced one more finding that inverts the comfortable narrative of ancient technological progress. The oldest cuts in the Aswan quarries, the ones that by their relationship to later work and to the prehistoric paintings can be placed earliest in the sequence, are the finest. They show the tightest dimensional tolerances, the smoothest surfaces, the most consistent spacing. The later cuts, the ones that can be confidently attributed to workers of the dynastic period using the tools we know they had, are rougher, less uniform, cruder in their precision, less impressive in every measurable respect. This is not how technology is supposed to work. Across the entire span of human history, the direction of travel in any technology is improvement. We get better at things over time. Successive generations build on what was learned before. The later work is supposed to be more sophisticated than the earlier work, not less. At Aswan, the sequence runs the other way. The most sophisticated stoneworking is the oldest. Everything that followed it is a gradual decline, as though a capability that once existed in this place was slowly lost, and the people who came after were doing their best to work in the style of something they no longer fully understood. None of what the analysis found was hidden. None of it required new excavations or newly discovered sites or any evidence that had not been available for a century. The scoop marks have been there for anyone to examine since the quarry was first properly documented. The deep, narrow shafts have been mapped. The microscopic textures of the cut surfaces are accessible to anyone with appropriate equipment. The prehistoric paintings lying over the cuts have been recorded in the literature. The sequence of work quality running from finest to roughest as you move forward in time is visible to anyone who looks at the quarry with sufficient care and sufficient willingness to follow what they are seeing rather than what they expect. What the Grok analysis contributed was the willingness to look without prior conclusions. The human researchers who have studied these quarries over the past century and a half did so within a framework that had strong reasons to explain the evidence in particular ways. The framework is not dishonest. The people who built it and who work within it are not engaged in deliberate deception. But the framework has institutional momentum. It has textbooks and careers and funding structures attached to it. When you have spent 30 years teaching a particular account of how the Egyptians worked granite, encountering evidence that that account is wrong is not simply an intellectual puzzle. It is a professional and personal disruption of a significant order. The framework protects itself through the entirely human tendency to interpret ambiguous evidence in ways that are consistent with what you already believe. A machine intelligence does not have that tendency. It does not have a 30-year investment in any particular interpretation. It does not have colleagues who would be embarrassed if the old explanation turned out to be wrong. It has pattern libraries and comparison functions and the ability to generate a numerical description of what it is examining without filtering that description through professional self-interest. When it looked at the Aswan marks and compared them against its knowledge of how surfaces get cut, it reported the closest match without hesitation. The closest match was not an ancient method. It was a family of modern precision industrial cutting processes that should not have existed anywhere near the Nile Valley at any point in the period these quarries were supposed to be active. What follows from that conclusion is genuinely difficult to sit with, because every possible explanation for it requires accepting something uncomfortable. If the precision cutting signatures at Aswan are as old as the prehistoric paintings suggest they might be, then whoever made them had capabilities that our current understanding of ancient human technological development simply does not account for. If those capabilities existed, they were subsequently lost so completely that no record of them survived in any form that archaeology has yet recognized. The civilization or people who possessed them left no obvious trace in the historical record beyond the marks themselves in the stone. They rose. They worked granite with a precision that modern industrial technology can match but that nothing in between the ancient world and the Industrial Revolution could have approached, and then they vanished, leaving behind only these smooth curved scoops in the hardest rock the Nile Valley offered. The alternative is that the marks are not as old as the stratigraphy suggests and that the prehistoric paintings are misleading in some way not yet understood. But that would require rewriting not just the interpretation of the quarry marks but also the established dating of the prehistoric rock art tradition in the region, which rests on independent lines of evidence. Or perhaps there is an explanation that no one has yet thought of, some method or material or process that falls within the range of what ancient humans could have achieved but that nobody has recognized as a match for what the Aswan surfaces show. That possibility should not be dismissed. Human ingenuity is not fully catalogued, and archaeology regularly surprises itself with discoveries that extend the known range of ancient capabilities. Perhaps the Aswan marks represent such a discovery, a technique that was real and human and ultimately recoverable through patient investigation. What the Grok analysis established with clarity is that the current explanation is not that technique. Pounding with dolerite did not make those marks. Something else did. The stone has been saying this in the only language available to it, the language of surfaces and curves and microscopic textures and chemical residues, for as long as anyone has been willing to look carefully enough to listen. A machine without any reason to look away finally looked carefully enough to hear it. The unfinished obelisk lies in its quarry in southern Egypt exactly where it was abandoned thousands of years ago, surrounded by those channels with their smooth repeating scoops, still attached to the bedrock that was never fully cut away. Anyone can go and stand over it and run their fingers along the walls and feel what the analysis measured in numbers. The curve is there. The smoothness is there. The impossible consistency is there. The question of what made it has been sitting in that stone for longer than recorded history has existed. Now at least, thanks to a machine that had no investment in any particular answer, we know with precision what the answer is not. What it actually is remains, for the moment, one of the most genuinely open and genuinely important questions in the study of human antiquity. The stone is still speaking. The question is whether the people studying it are finally ready to hear what it has been saying all along.